So last week we talked about the optical flow, which is for every pixel we will get a motion vector, the motion x and motion y with respect to previous frame. And we talked about this brightness constancy equation, which is fxu plus fyv plus is equal to ft. And we derive this assuming the brightness is constant from frame 1 to 2 if we make a small change in x, y, and small change in time. Then we talk about two different methods to compute optical flow given two frames. One was Horn and Shunk, and which uses the variational calculus and imposes two constraints. The optical flow has to be smooth. So we'd say ux square plus uy square and vx square plus vy square should be small. And then also it has to satisfy brightness constancy equation. This fxu plus fyv, minus ft should be small. Then we talked about another method which is more simpler and works pretty well. It's called Lucas-Conade, in which we are going to assume the optical flow locally in a small neighborhood is similar. Suppose if you look at a pixel and look at 3 by 3 neighborhood around it, then we will assume at all 9 pixels optical flow is the same. Then 9 pixel will give you 9 equations, 2 unknowns. We can do least square fit and come up with a very simple method for computing optical flow at every pixel. Now in this one, then we realize that, well, if the optical flow is small, or motion is small, then we can compute optical flow using these two methods. But if the motion is large, then we'll have problem. And the reason is that we are computing the optical flow based on these derivatives, spatial temporal derivative, fx, fy, ft. And I told you how to do that with our little masks, 2 by 2 or 3 by 3 masks. And they're looking at a small neighborhood. So they won't be able to distinguish if the motion is, say, 5 pixels and 1 pixel. They look the same. So therefore, in order to resolve that problem, we talk about pyramids. So what a pyramid does, it gets the multiple copies of same image, and if the motion at a original resolution is 10 pixel, next level of pyramid, the motion will be 5 pixel, will be half of it, and then it will be 2.5 and so on. So that helps us. So we talk about Laplacian pyramid and Gaussian pyramid and so on, and their applications. So today we are going to talk about in detail the motion models, which will help us to compute the global motion. And it will be a next lecture where we'll estimate the global motion, and we will give you a kind of course view of these different motion models. Then we will have another lecture. We'll go in more detail how to compute these different motion models more elegant way. So the idea here is that we will start that the 3D motion is happening in 3D in the real world. We are taking a video, and that is being projected in the video in the image plane. So optical flow is the motion in the image plane, but it is due to the motion in 3D world. Okay, so we want to look at, say, well, how do we come up with this model of a motion, how it is projected in the image plane. So we'll start 3D rigid motion. We'll talk about how we represent rotation, where the motion essentially is translation, rotation, scaling, and there are lots of these things. And so we have already talked about these two projection models, orthographic projection and the perspective projection. We will use those. And in order to talk about motion, we have these two models. One is called displacement model, where we look at the bunch of points in one frame and bunch of points in another frame, and we want to find out this point or this feature point. These points can be Harris points, how much it moved compared to the previous frame or next frame. So this point, say x1, y1, then the next frame, if it is x2, y2, then that's a motion. That's a displacement vector we can compute by finding the difference between x2 and x1 and y2 and y1. That's called displacement model. Then there is this other model which is called instantaneous model, which looks at the optical flow. Optical flow is which is like a rate of change of x and rate of change of y. they are similar, but there's a little difference. So now in particular, to represent the global motion of the two images from image 1 to image 2, there are these models. One is very popular, is called the affine transformation, and there'll be a parametric model we are going to talk about, and we will estimate that actually as compared to estimating optical for every pixel. And then there's a homography, a projective transformation, and we can then show that given the displacement model, then we can actually estimate the homography using the spine correspondences. We don't have to use the optical flow constraint equation. So let's get started. Now, say we have a 3D world coordinate which is shown here, x, y, z, and at time t1 this is what we have. When there's a motion, now this coordinate system basically changes. So it can translate, so origin can translate from here to here, and it can rotate. So any object, 3D object, its motion called rigid motion. Like a car is a rigid, it's moving. Person is not rigid, it's articulated. So we are not going to talk about that right now. So the rigid object, its motion in 3D can be described by 3D rotation, 3D translation. And to describe the motion, we are going to talk about the motion of a coordinate system. So we have a coordinate system x, y, z, and maybe there's an object here. We can describe each point in the object with respect to this. Now when the object moves, then the coordinate system moves with it, and that motion is described by the translation vector t1, t, and then the rotation, which is rotation on x-axis, y-axis, z-axis, how it is changed. So that's kind of rigid, 3D rigid motion. Okay. So in equation, this is what we are going to describe. So let's say we have a location in an object at time t1 is x, y, z. It rotates with this rotation matrix, and then translate, we get the next location, x prime, y prime, z prime. And the rotation is described by this 3 by 3 matrix. So we will take this x, y, z, multiply with the first row, and it'll become x r11 and y r12 and z r13, and we'll add translation to that dx. So that will be a new location after the motion. Similarly, we can find a y prime, which will be x r21, y r21 plus r23, z plus ty will be the y prime, and so on for the z prime. So that's what basically the 3D motion is. So this is called rotation matrix. It's a 3 by 3 matrix. There are 9 unknowns, 9 elements, and then the translation has also 3 unknowns: translation x, translation y, translation z. Okay. So now let's talk about how we can compute the rotation matrix. Let's say we want to rotate this vector. So this is our vector, and so locations x, y, z. The component on x-axis is x, component on y-axis is y, and then z. And we want to rotate this vector in the counterclockwise direction around z-axis. We want to do like this. Okay. So this vector will become like here, and z is going, as a perpendicular to the screen. So therefore, now we have a new location, x prime, y prime, z prime, and now we can look at, let's say this vector has a length r, uppercase R. Now when we rotate, its length does not change. If you take some object, rotate, length remains the same. So therefore, length of this vector will also be r. It won't change. Now let's say this vector was making angle phi with the x-axis, which is shown here, and after rotation this makes an angle theta, because we have rotated by angle theta around z-axis in counterclockwise direction. Okay. So now if you look at this vector, since it's x, y, z, so the component of this around x-axis is x, and then around y-axis y, all uppercase y, and the z. Now therefore we can see that actually we can describe x, this one, using this triangle as the r cos phi, because this is r cos phi in this triangle, and this will be r sin phi using this trigonometry relationships, okay, that you know. So we are looking at this triangle. Then let's look at this triangle where the angle is theta and phi. So now here also we can describe x prime will be r cosine of theta plus phi, okay, because a bigger triangle, and y prime will be sine of theta plus phi multiplied by r. So that's what we have here. X prime is r cosine of these two angles, y prime is r sine of two angles. Then we can expand these cosine of sum of cosine and sine of, sine of sum of the angles. So this will become cosine theta and cosine phi minus sine theta and sine phi. That's a trigonometry. And this sine will become sine theta, cosine theta, and then cosine theta, sine phi. So this is pretty obvious. You must have learned in the middle school. So now what we are going to do, that we will take r cosine phi and we will put as x, and r sine phi will put as y. So then this will simplify that now x prime is given by x cosine theta minus y sine theta, and y prime is given by x sine theta plus y cosine theta. So now we have the x prime y prime after the rotation in terms of the angle of rotation, which is theta, okay, and this can be written in matrix form. Now when we are rotating around z axis, then the z component of this vector will not change, only the x and y component will change, okay. So therefore z prime is same as z, because you multiply this with last row, this will become 0, this becomes 0, and this becomes z, okay. So that is the simple rotation matrix for rotating around z axis in counterclockwise direction by angle theta. So now another simple way to determine the rotation matrix around any of these principal axes is to do this. So we are going to assume that there is a unit vectors u, v, w, which is superimposed on these x, y, z, okay. So when we want to find our rotation matrix, suppose we don't do anything, so then we are going to just read what is the u vector here in terms of x, y, z. So since the length of this is 1, so it has component x, component is 1, it doesn't have y component, it doesn't have z component for u. So we are going to write down 1, 0, 0. Similarly, y has component 1 around y-axis, doesn't have component x and z, so it will become 0, 1, 0, and so on. So this is the identity matrix, which is there's no rotation. Now let's say now we want to rotate around the z-axis. So when we rotate, we are going to rotate this unit coordinate system u, v, w. It will become like this. So u will become u prime, because we are rotating like this in counterclockwise direction. V will become v prime, which is shown here. And since we are rotating on z-axis, z will remain same. The w will remain the same. So therefore, again, to get a rotation matrix, we'll just look at the new u prime. New u prime has two components, one on x-axis and one on y-axis, and doesn't have any component on z-axis. The component on x-axis is cosine of theta, because the length of this unit vector is 1. So we get cosine of theta. Component on y-axis is sine theta, and then z is 0. And look at v prime. It has component around x-axis, which is negative, which is this way because x is here, and then y-axis it has this component. So this will be minus sine theta, and the y-axis is cosine theta, and then z is 0. And then w and w prime is same, so it will be 0, 0, 1. So it's a pretty quick way to find the rotation matrix around any rotation and any principal axis. Let's say this is a rotation in the clockwise direction around the y-axis. So when we rotate it on y-axis, v will remain same, v will not change, but the u will become here because we are rotating like this. So it will become here, and w will become like this because w was here, and w prime will become other way, like that. So then we can again look at it, say this vector u prime has two components. One is around x-axis and other is around this z-axis, and so that will be given by cosine of beta, because this is around this axis, the x component, y is 0, and the z component, because this is, now we are going to look at x and z coordinate system, and that is become the sine of beta, which is shown here. And the y will not change, the v will not change, so it will be 0, 1, 0. And similarly we can come up with for this one, so this has the minus x component, the w prime, and doesn't have y component, and the z component will become cosine of beta, because we are looking at x and then z, and it has changed this way, so we'll look at these things. So this is pretty simple. You can come up with these rotation matrices around x, y, in counterclockwise direction, clockwise direction, just looking at these unit vectors, how you are rotating, and then reason about that. Okay, so that's the idea. Now, in order to define a rotation around any arbitrary axis, because whenever we rotate, we don't necessarily rotate around x, y, z. We can rotate around any arbitrary axis. So there's this thing called Euler Angles. So what we do, we say rotation on any arbitrary axis can be defined in three primary rotations. Rotation around the x-axis by angle phi, angle psi, which is this one. Rotation on y-axis by angle beta, and this one rotation on z-axis by angle alpha. So you have three rotation matrices. We multiply together and we get something like this. So this is the general rotation matrix. Yeah.
In the previous slide, the equation was something different for y in the previous slide. Rotation for the y-axis, the sine.
This one?
No, the matrix I'm talking about.
This one?
Yeah.
Yeah.
Should the minus component be down or should be up?
So here, see that we have x and we have a z like this. Okay. So now the x, positive x is like this, and the positive z is like that. So so we are looking at, you mean that this last column?
Yeah.
Okay, so that is the w. So which will be w prime. So it's like this and like this, and so u from the here it becomes like that. We are rotating this way. So then we had this thing, so it will become something like this one, right? It's moving other way. So that's what we have shown here, which is the w prime. Okay, so now in this case we will have x and z. This positive z is this way, and negative z will become like this, and positive x is this way, and negative x will become like this. So if you make a figure like that, then we will have this way, and it will have negative x, because see this thing, this is a positive x, this vector become on the other side of x, so that's why it's a negative. And then z is the same direction, it will become positive. So you can verify that yourself, but I think this is correct. Okay, so getting back to Euler Angles, so we have these three rotation around principal axis: the x-axis by gamma, y-axis by beta, and the around z-axis we have alpha. We take these three matrices.
Signs here are reversed.
Yeah, so you see that there we are doing that in the clockwise direction. When you rotate in the clockwise direction, it's different than compared to when you rotate around counterclockwise direction. So I gave you examples here of any kinds of rotation. So here we have rotation around clockwise direction. So that's what we have, this one. And here just for example, we rotate around clockwise direction, so they will change. And from this it's clear that if you want to find the inverse of a rotation matrix, So you can take this matrix and just change the sign from theta to minus theta. So it'll become inverse, and you can multiply together, it'll be identity. Okay? So so now what we have here, this Euler angle rotation matrix, which is a 3 principal axis, principal rotations. These terms are pretty messy. You know, they are non-linear, and you know, they're pretty messy. So now what we will do, we will make an assumption. We are going to say that these are very small angles, okay? And which means that we are going to say when the angle is small, cosine of theta will become very close to 0, and cosine of 0 is 1. And then when angle is small, sine of small angle is sine of small angle is 0. Okay, so therefore then it will reduce, sine of theta will reduce to theta. So these are the approximation we are going to do. If the angle is small, cosine of small angle is 1. If the angle is small, sine of small angle is that angle, that value. Okay, so if you do that, so for example, this will become 1, this will become 1. So we will have, instead of all, this will become 1. Okay, now if you look at this one, we have say let's look at this term. We have cosine, so it will become 1, and we have a small value beta, small value gamma. So when you multiply the small with small, all this will become even smaller, so we can get rid of that. Okay, now here this will become 1, and when angle is small, then sine of alpha will become alpha. So therefore this whole thing will reduce to minus alpha. Okay, if you look at this one, so this is small, multiplied by these together, this becomes 0. This cosine will become 1, and this will become beta, and this will become 1. So that's why we have beta. So you can simplify all this. So all these monster terms actually will reduce to this nice matrix, and that matrix is called the Euler angle. The assumption is that these angles of rotation are small. Okay, so that's one thing. Now given this, then we are going to look at the motion, the projection of this motion on the image plane, because see, that's what we are interested in. Computer vision, we work with images, and these are the projection of something happening in 3D. The object is moving in 3D, our camera is moving in 3D. There's a motion, we describe how to describe that rigid motion, the rotation and translation, Euler angles and all this thing. Now they are going to be projected to the image plane, and we are going to talk about, you know, how we model that. So displacement model. So again, we have been talking about these two models of images. One is orthographic projection, where that we take the x, y, z, and we get this projection, and it is the same thing. Maybe this equation didn't show up here, I think. There were equation, I guess. Anyway, so again, as we talked about before, x, y, z will map to small x, small y. So there won't be any impact of the image plane. And orthographic projection, when we are taking a picture from the very far distance, like a UAV, and then it will not matter that how far you are. It's a very simple model. Now if you want to use orthographic projection in this motion model, so this is what we already have. We have the rigid motion in the 3D. Then orthographic projection means the x coordinate of in the image plane will become x coordinate in the word, or a scale multiple of that, and y coordinate similar. So therefore, and that's what it's saying, image coordinates and what coordinates. So if you take this, get the x prime will become this multiplied with first row and plus tx, and y prime will become this multiplied with second row, like that. And we are going to simplify this, and we are going to call this one a, b, and this will just lump into just one translation, which is b1. This is a translation x and translation y. Now this is like a starting point of a simple model called affine transformation. Okay, so that can be written like this. We have a 2 by 2 matrix, and we have x, y in the first frame. These are the x prime, y prime in second frame, and this is a translation. So this has 6 parameters. from motion from one frame to other frame is described by this formula. You plug in the value of pixel xy, it gives you where it go in the next frame, give you x prime, y prime. So it has these metrics which kind of capture our rotation and other things, and it has a translation. Okay, so for simplification we will say x prime vector is equal to ax, which is a matrix A and vector x and plus b. Okay, so that's called affine transformation. Actually we are going to use that a lot. Now the another way to do this affine transformation also, that we'll use the Euler angle for the rotation. In the previous one we used the nine element and the rotation matrix. So this is another way to talk about that x prime is given by this multiplied by first row and this multiplied by second row, and then again we can simplify like the affine transformation. So now if you look at the perspective transformation, there the z matters. You know, the orthographic z does not matter, the depth, the distance from the camera. So the y is given by minus fy upon z, y coordinate of the image, x is given by minus fx upon z. Using this, we have talked about this before. So f is a focal length, which is a distance from the camera to the lens, the image plane to the lens, and z is a distance from the camera to the object, and this is a point, and there are two triangles, they are equivalent, and we can write down like that. So this is a very simple pinhole camera or the perspective projection which we are going to use. So now if we have the 3D rigid motion, again the rotation matrix by 9 unknowns and 3 for the translation, we expand this, so x prime become this multiply with first row plus dx y prime, and so these are x, y, z are the coordinates in 3D in the first time t1, and x prime, y prime, z prime are the coordinate in time t2. So now we are going to take pictures. That first picture will be the small x, small y, and second picture will be x prime, y prime, small x prime. So here let's say we assume focal length is -1, then given the coordinates in the word, we can find out the coordinates in the image by using this formula minus f x prime upon z prime. F we have assumed to be -1, so it will become x prime, the image coordinates will become word coordinate x prime and z prime, and similarly y prime. So that's the way we are doing the projection of the word to the image. Very simple model. So now looking at this thing, so we are going to substitute x prime here and divide it by z prime here, and divide every element by z. So this will simplify to this one, because if we divide by z here, become x upon z, and that will become small x, y upon z will become small y. So we are, by dividing by z, we are converting the word coordinate to image coordinate, because that's what it is. So that's why we get x here, y here, and z divided by z is 1. So we'll just get R1 3, and tx divided by z is like that. And the z prime also will divide by z, so it will become x upon z will be small x, y upon z will become small y, and this will become R3 3, and then tz divided by z. So this is a very simple thing. Now we have the image coordinate in second frame, x prime, y prime, in terms of the image coordinate in the first frame, x and y. But again here we have the z and the translation in x, which is in 3D. So now one thing you will notice that this is the kind of two factors there. We have a tx and we have a z. Okay, so tx is a translation in in x direction in 3D, and z is a depth. So there is ambiguity because it's a ratio, so we can change one and change appropriately second one, then will not make difference, it will be the same. So Therefore, there's no way that we can get rid of this scale ambiguity, to distinguish between the translation and the depth. So what we are going to do is now look into, let's say the pictures we are taking, the picture 1 and picture 2 of a scene which is a planar, which is a plane. Like this wall is a plane. Okay, so we take a picture of this wall, and so therefore for that scene we can define an equation which is the equation of plane. Ax plus by plus cz is equal to 1. That's the equation of plane. So that helps us to get rid of z now. Because see, in the previous equation we have z, and that's the problem. But in image, when we have images, we don't have z. We have x and y. That's it. It's a 2D. But the word is 3D, that's what we have z. So we take an equation of plane, and we can write down like this. So x, y, z vector, and ABC, which is the orientation of surface normal of plane, should be 1. If you multiply this with that, you get this. Then we have the rigid module, which is the x prime, y prime, z prime is given by rotation, and the x, y, z plus translation. So we're going to combine these two, and we will put this thing, the equation of plane, since this whole thing is equal to 1, we can just put it here after t. It doesn't matter. Okay? So we just put it here, since the whole thing is 1. Now we have x, y, z here, x, y, z here, so we can simplify and put this thing in a one matrix where we have r and plus t and abc. We take common x, y, z. So in the first one we have rotation, second one we have this. So that's why we'll call this A as a big matrix, which is consists of this. And now we have a simple relationship. X, y, z multiply some other matrix A, which contains a rotation matrix, which contains the translation vector, which contains the surface normal of the plane. So which is good. And so that again tell you that if I know the 3D word coordinates in frame 1 or time t1, which is capture frame 1, then 3D coordinate in frame 2 or time t2, which is x prime, y prime, z prime, I can relate them by this A matrix. And so we can simplify this. Now the first x prime will be given by multiply this with the first row of the A matrix, which we'll call A1 to A9. So A1, A2, A3 first row, second row, third row, and simple multiplication. So now from here, then we want to find out the image coordinate, which is x prime, y prime. And according to the perspective model, image coordinate x prime will be x prime, uppercase x prime divided by uppercase c prime. That's a perspective projection. Focal length we have assumed is -1. So that's what we have been using. Okay. So that's what we are going to do. So we'll take this one, divide by z prime, which is this one, take y prime, this one, divided by z prime. So that's good. Now from here, we are going to get the image coordinates, divide everything by z. So we divide by z here, it will become small x, divide by z here, small y, this will become just a3, and similarly this will become x, small y, and so on. And same way for y prime. So now here we don't have anything with respect to z. We have everything in terms of the image coordinates. X, y in the first frame, x prime, y prime in the second frame. Okay? So which is good. But we are able to do that because we assume the scene is planar. So we use that fact to simplify this. So now one thing you will notice that this is again is a ratio, so ratio of the first row with the second row. So to define this motion, we need to find out these 9 unknowns. If we can find these 9 unknowns, then we know motion from one frame to other frame, because we can take any point in the first frame, which is x, y, plug in these equation, we get similar point in the next frame, x prime, y prime. That's the idea of motion. Okay. So now we won't be able to find unique values of all the 9 unknowns because they are in a ratio. So I can take any value, assign any value of say A3, and then take a multiple of that, and then I can multiply that value by some constant and multiply same thing here, then they will cancel each other because it's a ratio. So that's a problem. So there's no way you can find out the unique value of all the 9 unknowns. So therefore we have to arbitrarily select one of the unknown. A9 will become 1. So the same idea of this scale ambiguity I talked about earlier, that we have the ratio of the translation in 3D and the depth, and there's no way we can determine both. So we'll have to use that. So we are going to say A9 is 1. Okay. So now what we have is this transformation, which is a very popular transformation from one frame to other frame, and it is called homography, or it is called the projective transformation. And we can write down this in terms of matrix and vector. Okay, so this A is defined like this, similar to affine transformation we have. The vector B is defined like this. This is like a translation vector, and C is another vector, A7, A8. So this is exactly same here. So we have just put this in a matrix and vector form. Okay, and as you see, if I multiply x, y with first row, become A1x plus A2y, which is this one here. Then it is aided by B, so first element of B is A3, which is this row. And similarly for y, multiply this with second row, it will become A4x plus A5y, this one, and then aided with the A6, which is this one, the translation. And similarly, if you can do for the C, because we have C here, this vector, we have a C transpose, so it will become A7, A8 will be a row, and that is multiplied by X, which will become X A7 plus Y A8 and plus 1, which is 1 here. So it's the same thing. So now we have this in a matrix form, and this is called projective or homography. And as you see that the affine transformation is a special case of this, because if you assume C to be 0 vector, this whole thing will disappear. We'll get affine x plus b. Okay, so affine has 6 unknowns. This is 8 unknowns. Okay, so 8 unknowns are these A's, these all A's. So this is like a rotation, all other things. This is like a translation. This is this other C vector. Okay. So now let's say we want to, given 2 images, and let's say we have corresponding points. We know the points here, we know the points here, we know this point belongs to this one, this point belongs to this one. Then the idea is how can we compute the transformation, the homography between 2 frames, or the projective transformation. So it's very simple to compute, and we are going to do that using what least square fit, as we did in Lucas-Conade algorithm. So again, to review the least square idea, so let's say we have a bunch of points and we want to fit a line to that. So this is the equation of line, y is equal to mx plus c, and we have several points. Let's say we have n points. So if we want to fit a line to those n points, then each of the points should satisfy the equation of line. So therefore we put in the value of x1, y1 first point, x2, y2 second point, third point, nth point, xn, yn. In all these n equation, there are 2 unknowns, the slope and intercept, m and c. So we can write down this in matrix form. We'll multiply this with the first row, we'll get first equation, multiply with second row, like that, multiply with last row, we'll get this. The same thing, very similar to what we did in Lucas-Conade. And this will become big matrix A, this vector P and Y, Now we cannot invert this, so we will multiply by transpose, and then A transpose A we can invert because it's a square matrix, and this whole thing is called pseudo inverse. We talked about that, and this is the way we will get the equation of line, which means we'll get these two unknowns, the slope and intercept. And this way to do is called least square fit, because what it's doing is minimizing the error, and this error is given here, and we are squaring the error, and we want to minimize that, which means a least square error. And we're saying that we want to find these parameters m and c. If they are ideal parameters, then this should be 0, because the equation y is equal to mx plus c, they are 0. So all these are 0, and that's the minimum value you can get. But they may not be 0, because the approximation may be small number. Small number can be positive, small number can be negative, so we square it, we minimize that, and that's the way you can get this least square fit. So we're going to use the same idea to fit the homography between these two frames. So let's say we have two pictures of the same scene, they're little translated, rotated, and say we identify, say, these points using, say, Harris detector, and then we match them. Say, well, this point matches with this, so we get a descriptor around here, shift descriptor, and we find out you match shift descriptor with this one, with this one, with this one, this one. We find the best match between two shift descriptors here. Similarly, we do for this point, and so on. So if we find these matches. Now this is x1, y1, x2, y2, x3, y3, x4, y4, x5, y5, and this is x1 prime, y1 prime, x2 prime, y2 prime, and so on. So with these two sets of points, okay? So we can just fit those. So, if the points are like this is a transformation we have, and we can rewrite this like that, multiply this with that, and become like this. And we have two equations for every correspondences, okay? So in these two equations, we know x and y and x prime, y prime, because we know these location. We just did it. So unknowns are A1 to A8. There are 8 unknowns. Okay. So we get 2 rows for each of the point I, and we can write down this in this form. So if you multiply this with that, then we get A1 xi, A2 xyi, and A3. And then you will get this one, these 3 here will become A8, this one, and so on. So these are the one of the equation which is shown here, and then you will get another equation with respect to y. So let's say this was x1, y1, I is equal to 1, and this is x1 prime, y1, x1 prime. So this is one of the equation. So and we'll get a1x and a2y and then a3, so which is these terms, okay, a1x, a2y, a3. Then these are the first 3 terms. Then a4 is 0, a5 0, a6 0. We want to get that. Then we have a6 multiplied by x prime, okay. Then a7 multiplied by y and x prime, and then we will have, I think there's one missing here. So as you see that we have a7 multiplied by x prime, which is this one, a8 multiplied by y and x, which is here, and then we need to have one more term which in this one is missing, which will be that. So we'll get first equation for the x from here. And if you do the same thing for the y, you'll get the second equation. So like that, we can put in these 2 equations for every point. So suppose you have 5 points there, so we'll get 10 equations like that. One for x, one for y, one for x, one for y. We have 10 equations. So then we have here 8 unknowns, and we can find out using least square fit. Yes?
It's true because the last term is on the other side of the equation.
Yes.
So,
Yeah, you're right. That this one, you mean this term?
yeah,
Because we already multiplied this x prime.
yeah, because the x prime is on the right side of the equation. So
Oh, okay, yeah, you're right. Okay, good. Yeah, I think this is correct. Okay, so that's nice. So what we are doing here, we have x prime on one side, we are bringing these on other side. So as you see, this a1x, a2y, a3y all positive. That's what we get from here. a1x, a2y, and a3, which is here. Okay, and these other terms will become negative. That's why we have a negative point. So we bring in on this side. So that will become x prime x. Okay, so that's what we have, the a7 multiplied by x prime x, and a8 multiplied by y x prime, which is this one. So that's correct, and we can do the same thing for the y, which is the a1, a2, a3 all are 0, so we don't have any terms with respect to a1, a2, a3 here. Then first term we will have a4, which is x, a5 y, and a6, which are these terms, and then these will become minus, so this will become minus a6 xy, and no, a7 minus a7 xy, and then a8 y prime, which is these terms, and the this way we will have this correct, because I should write down the another row where we put the x on this side and rest of terms on this side. Okay, so that way you can actually do this least square fit, as we have been doing for the Lucas-Canade, we've been doing for a straight line. So you have many equations, few unknowns. Again, we take the transpose of this, multiply, and find the inverse, and this is a solution, which is the homography of these two frames. So that's nice. So now to summarize, we have the displacement models. The simple motion in the image plane is translation. You just take x, y, and translate y b1, b2. So x prime become x plus b1, y prime become y plus b2. Simple thing, image displacement. Then rigid motion is that translation in x and y, which is b1, b2, and the rotation on z-axis, and that is the rotation by angle theta, and that's what this is, rigid motion in 2D. This is all are 2D motions. Then the affine transformation, which is more sophisticated, which includes everything, the translation, rotation, and scaling, and all this thing, which has these 6 unknowns. These are the 4 unknowns in that rotation kind of matrix, and these are the translations similar to this. Then the projective transformation or homography, it is 8 unknowns, and this is what we have as we just explained. And this either will have a1 to a8, or we'll say a1 to a4, then b1, b2, and then c1, c2. It's the same thing. And this is a special case of the affine is special case of this, because if c1, c2 is 0, this is exactly same as we have here. Okay. So now there are some simplification, some approximation of the homography or projective transformation, because this is a non-linear. See, whenever you have a non-linear thing, whenever you have this ratio thing is a non-linear, and that becomes a problem. So so we can approximate this by some model called biquadratic. So again, we are going to do Taylor series, and you are going to do this in homework. If you do the Taylor series of this, and you will get like that up to second order. That's called biquadratic. So it's a quadratic, but it's a 2-dimension, x and y. So this is the biquadratic model. Again, given x, y, we can find out that point in the second frame using this formula if we know these 12 unknowns. So this is more complicated because there are 12 unknowns, but it's a linear. Okay, it's not, doesn't have this ratio thing. So then there's another approximation of this where we are going to get rid of the square terms, and we'll just put these linear terms, and they are linear in 2 dimensions, linear in x and y. So this has lesser unknowns, 8 unknowns. And then there'll be pseudo-perspective model, which will be again simplification of this, and this will have also 8 unknowns as compared to 12 here. So what we are going to do here, this A4 will be the coefficient for the y prime, same A4 coefficient will be for x squared, and similarly for A5 and here. So these are different models, and we'll go in detail, talk about, and there'll be homework, but this kind of give you an idea. So translation is the very simplest model. It's a simple, and we can do this correlation matching as we talk about, like MPEG. That's what they do. Each 16 by 16 block, they find out the displacement, and does not capture the zoom, does not capture the rotation, does not capture pan tilt of a camera. It's simple translation. Rigid has a rotation and the translation. That's it. Okay. No other rotation. Rotation is a rotation around z-axis. But when you do the scaling in z-axis called zoom, pan tilt is rotation on y and x-axis, so it's not there. So affine is much more general than the previous models. It has a rotation around the z-axis. It can not capture the rotation on y and x-axis. It is valid for the orthographic projection. And projective is more general than affine. It has 8 unknowns, but it's difficult to estimate because of denominator, and we're going to talk about how to deal with that. Okay, and then these are the approximation models of the projective. The biquadratic, which is obtained by second order Taylor series. It has 12 parameters as you saw, and bilinear is another approximation where we are going to remove some square terms, and it's 8 unknowns, and it is used a lot in the interpolation. We are going to talk about that, but doesn't relate to any 3D motion. And then there's a pseudo perspective, which has the again 8 unknowns, where we remove the square terms and we make these A4 and A5 same in the x and x prime y prime. So this is this example, and when you have translation, you just translate the block. Rotation rotates like that. We can have rigid transformation, which is rotation and translation. Affine can capture all of these, in shear that you kind of scale in different proportion. So that all that was on the displacement model, where we have x, y in first frame and x prime, y prime in the second frame. Now there's a parallel model which is very similar to this, called the instantaneous model, which is capturing the optical flow. Okay, so we're going to talk about that now. So again, here we are going to look at the 3D rigid motion. Yeah, go ahead.
So about the model that we had 8 unknown,
Yeah.
we need to figure out the values for them. So at least we need to have 4
points.
Points that SIF gonna give.
That's right. Yeah. Yes. At least you need 4 points.
Using different subset of all the interest points that SIF will give us, the results will change.
Yes.
And how we can figure out what 4 of them are best.
Hey, do you know where is this thing? Can you do that? Just 1 second. That's so strange. Huh? The side there? Where is it? Try there. Yeah, I think it will reach. Yes, so I think that's a good question you are asking. So he's asking that, well, if we have only 4 points, so this system we got, which we had here, this system. So see this system, for each point it give you 2 rows. So let's say we have 4 points, will give you 8 rows, and this is 8 by 8 matrix, we can invert it. Or if we have, say 10 points, then it will give you 20 rows, so it will be a 20 by 8 matrix here, the A matrix, and we have 8 unknowns. That's not a square matrix, we can do a transpose, we can pseudo inverse, again we can find these 8 unknowns. Okay, so the question you're asking, say, well, if you have, say, 100 points, so one way is that, well, use all 100, you get 200 by 8 and solve that. So that's a standard least square fit. But other way, which we're going to talk about, what is called random sampling and consensus, or RANSEC, where you randomly choose 4 points from those 100 points and come up with a solution. Then you again randomly choose another set of 4 points and get a solution. You keep doing that, and whatever the best solution you get, and you take that one. Because what's going to happen in the least square, the problem is that if you have an outlier, you have points that, like, you want to fit a straight line, most of the points are like this, so you can fit a line, but there's one point there which is completely out of way of this line. So if you use all of the points, you don't know which one is wrong. So if you use all of the points, least square fit will give you completely wrong line, because it's very sensitive, it will kind of bias to that one point. So to deal with these outliers, least square fit, one has to do this fix, which is called the RANSEC, that you have to intelligently select the points you are going to use to find a solution, and then to deal with the outliers. So we are going to talk about that later. But right now, let's say there's no outliers and all the points are the same of the transformations. I showed you 5 points, then we can get the solution. Okay, so let's go to this thing. Hopefully we can finish this about the instantaneous model. And so again we have a rigid motion, so we are going to use Euler angles, so we have x, y, z, and so on. And so we can break this into 2 matrices. We have here we have on the diagonal we'll put zeros, and then minus alpha, beta, and all these the same, but we are going to take this and make it identity matrix. So if you take these 2 matrices, add them together, you will get this, because it's true. 0 plus 1 is 1, minus alpha plus 0 is minus alpha, beta plus 0 is beta, and so on. This is true. So we take the Euler angle matrix and break in 2 matrices for convenience. So then now this thing here, we have we can multiply this with the identity matrix, it will become x, y, and z. So you get another vector here, x, y, z. So we can bring that vector on this side. Okay, so we had here x prime, y prime, z prime. Now since we are going x, y, z, we'll move the other side, will become minus x, minus y, minus z. That's what we have. And this is the same thing we have here. And then x, y, z, and dx, dy, dz. Okay, so we have little like a different system here compared to this one, and that's what we are trying to do. Now we are going to find the velocity, the change in x and y and z. We'll call this x dot, y dot, z dot. So these angles now will become rotational angles, and we will call them the omega. And this is omega 1, omega 2, omega 3, correspond to alpha, beta, gamma. So this is kind of getting into instantaneous model as compared to displacement model. So now we have this instantaneous 3D rigid motion model, which is x dot, y dot, z dot. And the 3D is given by these these angles, and then the velocities v1, v2, v3. So this also is written like that. We have x dot vector, then we have this rotation angles, and then we have the cross product with x, and then plus v. So you can verify that if you expand this to cross product of vectors, you'll get like this. Okay, so that is nice. Now what we are going to do to go to the optical flow, because x dot, y dot, z dot, they are like let it change the velocities in 3D. Now we are going to project them and look at the velocities in 2D. So if you use orthographic projection, x, uppercase x is like small case x, uppercase y is like small case y. That's what we have been talking about. They don't change with respect to z. So therefore it is simple that this optical flow in the image plane will be u and y, v, and this will become essentially omega 2z, omega 3y, and v1. And then for the perspective projection, now x and y will change, will depend on z. That's what we have been talking about. So if I want to find out the rate of change of x with respect to time, which is the u, and we will call this x dot, then this function I have to differentiate with respect to t. So this is a numerator and this denominator. Then we know to differentiate this kind of function. You first square this, the denominator, then you keep this constant, and keep the z constant and differentiate the numerator, which will be f x dot, okay, minus, then keep this one numerator constant fx and differentiate the denominator, which is z dot. So that's a standard thing of differentiating the function, which is the numerator denominator. Okay, square the denominator, then keep the denominator constant, differentiate the numerator, which is this one. This is a constant, this is x dot, minus keep the numerator constant, which is fx, and differentiate denominator z dot. So differential, we are saying just a dot, which means differential after z with respect to all these derivatives with respect to time. So then we can simplify this. This will become f c divided by z squared becomes z x dot minus f and x upon z will become small x, and then z dot upon z will be like that. So we are starting to put the image coordinates here because we have x upon z here, so we put small x. That's the definition. And we have these derivative of the x, y, z in terms of dot. So similarly, if you differentiate the y here, so again you have a numerator denominator, so square of the denominator, keep the denominator here, then differentiate this will become y dot, minus keep this one same and differentiate denominator, which will become z dot, simplify, become f y dot upon z, and this will become y upon z will small y, and z dot upon z. So that is, now we are getting into the perspective projection, and we are deriving the optical flow equations in the image plane. So here now also we know from the previous model that x dot is given by this, y dot is given by this, z dot is given by this in terms of the omega 1, omega 2, omega 3, and v1, v2, v3. So we are going to introduce those. So if we introduce x dot here, from here, y dot from here, and z dot from here, and simplify, you're going to get these very famous equations. This is saying the optical flow UV in terms of 3D motion, the omega 1, omega 2, omega 3, which is the rotation, and v1, v2, v3, which is gave the translation velocity. The omega 1 to omega 3 are the rotational velocities. And then we have z is a depth, which is a distance, and x, y are the image coordinates. So these are two very famous equations which are used a lot in the perspective transformation. So now if we assume again here, say, because z is always a problem. The image plane we don't have a z. That's a problem. So let's say we have a planar scene. So we are going to use the equation of plane. which is this one, as we have did before, very similar to this. So then we can take this equation for the orthographic projection as we did before. Then we can simplify the according to this, and you will do this in the homework, that we can write down u is equal like this, v is equal like this, and this essentially is a affine transformation. As you see that we have xy here, and then we have these constant b1, b2. So given these two equations we derived before, using orthographic model and using the planar assumption, you can easily derive these equations where the b1 is this, a1 is this, and all this thing, and this is the affine transformation using planar assumption, orthographic projection, and instantaneous model. Now the optical flow is affine of the xy. In the displacement model, x prime, y prime was affine of xy. So there are two differences. Okay? In the previous model, we have given x, y, x prime, y prime. We relate them using affine. Here, we are giving x, y, and we are saying optical flow is UV is defined affine transformation of xy. So there are two different things, and even though they are related. So that's what you want to make a distinction here. So I don't know how many more slides I have. So let's maybe go a little over today. So now we can do the same thing for the perspective projection. Okay, so we did before the orthographic projection, assuming the planar. So then these are your two equations, and now we are going to use this assumption of the plane. So we can rewrite this like this, and if you substitute all that, then this will become like this. And this, if you remember from the previous one, this actually is the pseudo perspective model. Okay, so this is a pseudo perspective model. The optical flow under perspective projection using the planar scene is the pseudo perspective model in terms of xy. Okay, because here we have again the 8 unknowns, and using these equations, using the planar assumption, you can derive that. That will also be a homework. So then I think we are kind of done as a very broad run through these different motion models in 3D and their projection in the image plane. So in the image plane, in these two models, the instantaneous model, which is optical flow, which is in terms of velocities, the displacement model, which is in terms of the locations x, y, and x prime, y prime. And in both of these, we have to assume what imaging model we are using. Is it orthographic or the perspective? Orthographic is very simple, but it may not be realistic. Perspective is more realistic, but it is complex because it's a x upon z and y upon z. There's a denominator, so z comes in. So given all that, then the next time we are going to talk about given two images, how we can compute the affine transformation between two images. So they'll be different than computing optical flow, because optical flow is that for every pixel we are computing a vector. But here we are going to come up with these 6 parameters for affine, or 8 for the pseudo perspective, and that will define optical flow for every pixel. Because here if I put some value of xy, for that pixel I'm getting optical flow. I take a next pixel xy, I'll put in here, I'll get optical flow. So this is a parametric model. This will give me equivalent information of optical flow, but it's a more compact model. It is giving this defined by 6 parameters. If I have 1 million pixel to define optical flow, I need 2 million numbers, because for every pixel I need 2 u and v. if I fit this, the pseudo perspective affine model, for affine model I need only 6 parameters. Okay, for the pseudo perspective I need 8 parameters. So that's pretty interesting thing. So we're going to talk about that on Thursday. Okay, so we'll end it here.